dynamic process of the universe that is star formation. As we all know that the stars are the source of light and energy, now we are surviving on this earth is mainly because of one of the star that is sun, which itself explains the importance why one should study it. The star formations happens in the interstellar space containing a clouds, which contains a dust and the gases. The size, next slide. The size, the size of these clouds are much bigger, more massive, and they are more than a light years bigger. These clouds are held together by gravitational force, which is in hydrostatic equilibrium with the force exerted by the gases. These clouds of gas and the dust is called the nebula. Next slide. They collapse under their own gravity, and the cause for may be the simple random fluctuation due to the black holes or the nearby star formation. This disturbances compresses the gas and dust. That's the beginning of the first stage of the star formation, that is a protostar. Next slide. The core
என்னடி
of the
படிச்சது
the core of the protostar is not yet hot enough for the fusion to take place. Hence, can't call it as a complete star. It's just like an embryo in a womb. Protostars are usually surrounded by a dust which blocks the light that they emit, hence it is difficult to observe them. The gravity begins to pull the gases together, which causes the protostar to heat. As a result, it emits a radiation. However, as the protostar pulls in the matter and gets more denser, much of the radiation trapped inside eating the protostar. As the protostar generates a magnetic field, the magnet
சப்டைட்டில்ஸ் ஆன் பண்ணி பாக்குறேன் பழகு சப்டைட்டில்ஸ் இல்லாம ஐஎல்டிக்கு யூஸ்
as the
ஆகும்
protostar generates a magnetic field, this magnetic field generated causes a stellar wind. Some of the protostar even emits a jets of gases, usually along the rotational axis of the protostar. Eventually, the winds and jets clear the dust around the protostar, and it enters a main stage called main sequence star. The temperature exceeds 10 million kelvins, which is required for the fusion to take place. Now the fusion reaction takes place, which leads to the formation of helium. Now the core is mainly dominated by the helium. At this stage, the core shrinks, burning a hydro burning of hydrogen becomes relatively faster, and it causing a radiation to emit outward, push the outer layer. Hence, the star starts growing, passing through a subgiant stage until it reaches a red giant stage. Next slide. After almost all the hydrogen is used, core gets even smaller, hotter. At this phase, the heavier hydrogen fuses into a heavier nuclei like carbon and oxygen. Now, helium becomes the source of fuel for the star. The core is dominated by the carbon and oxygen, and a shell of helium around the core, and the thin layer of hydrogen around the helium. The core collapses due to a very little fuel to burn. The star enters a asymptotic giant branch. In this stage, stars grows rapidly and becomes a red giant star. Again, until the last burst of energy ejects the outer layer. This ejected layer is called planetary nebula. This becomes available for star, another for the formation of another star. The left behind core is very hot. It gradually cools. No more, there is no more fuel to burn and not at hot enough to fuse the atom. So it contracts further until we're left with a white dwarf. The maximum mass of the white dwarf is known as Chandrasekhar limit, that is 1.4 solar mass. It gradually cools to become a white dwarf. The process, this process is happens for the star less than the 3 solar mass. For the stars which are greater than 8 solar masses, the initial process is similar to that of the lower mass star, that is, clouds forming a nebula and all. For since it is more bigger, there more gravity. This gravity pulls inwards and becomes much hotter, which leads to the further fusion and greater outer pressure to counterpart the inward gravitational pull. As the fuel is running out, the the core converts and producing a more energy. So star again starts expanding and the core compressing. It gets even hotter. It starts fusing a hydrogen to carbon, carbon to oxygen until iron. Iron is referred as a nuclear ash. No star left with Now the star left with the iron core, which is more stable. Further fusion is not possible and the gravity dominates and the star collapses, ejecting all the heavy nuclei into the space. This event is known as supernova, and it leaves behind a dense ball of matter. It is so dense that even a electron in its quantum orbit falls into an atomic nuclei, which gives birth to a neutron star. If the collapsed core has a mass more than the three solar mass, it becomes a black hole. Still, the boundary between the neutron star and the black hole is yet the puzzle to be solved. Next slide. Neutron star. A neutron star is one of the extreme creatures in the universe. It is highly dense and it has the strongest gravitational force. Even light bends around the neutron star. Like a black hole, so it also creates a gravitational lensing effect. Like planets, neutron star also contains a solid crust over a core. The core of the neutron star is very hard. The outer layer is made up of a leftover iron from the leftover supernova. Iron exists in the form of crystal lattice and the sea of electrons flowing through them. Gravity squeezes the nuclei together. We find a fewer proton, as most of them merge into a neutron, until we reach the base of the crust. Here, the nuclei are squeezed. This phase is called Goyanki phase. As we go more deeper, the proton and neutron rearrange, making a long cylinder and sheets shaped like spaghetti in lasagna, which is called nuclear pasta, which is so dense that it is said that it is the strongest material in the universe. These lumps can make the mountain, which is of the height of few centimeters but are more dense than the Himalayas. Beneath the beneath this, there is a core here the proton and neutron may dissolve into a subatomic particles like quanta, but it's still a big challenge waiting for explode. The spin of neutron star is very fast than the parent. The fastest neutron star known is PSR J1748 2446 AD. It rotates at the rate of 716 times per second. Neutron star also have the strongest magnetic field of many of the known object, black holes. Next slide. Like a neutron star, black holes are another extreme creature found in the universe. Most of the black holes are formed from the remnants of the largest star formation, the dice of the supernova, as we already saw. Scientists can't directly observe the black hole through a telescope. However, the presence of the black hole can be studied by detecting their effect on the other masses nearby. Like if the black hole passes through a interstellar cloud, it may draw matter inwards. If the normal star comes closer to a black hole, it tears a star apart and it pulls it into inwards itself. As the attracted matter accelerates and eats up, it emits the X-ray that radiates into a space. Black holes are the region in the space where the force of gravity is so strong even the light can't escape through the boundary of the black hole, which is the event horizon. There are various classes of black holes, like stellar black hole, which are formed from the collapse of the star, which are typically a mass of sun. Supermassive black holes, their formation is still a topic under study, which are mostly found at the center of galaxy. Spaghettios A star is the supermassive black hole at the center of Milky Way galaxy. Now, I would like to hand over the presentation to the reader. Thank you.
Am I audible?
Yeah, you are audible.
Okay, so hello, I'm Rida. I'm here to discuss the characteristics and unique properties of neutron stars and black holes and their gravitational effects on their surroundings. So the next slide, please. Okay, so as the star dies in a supernova explosion, as discussed previously, this produces either a neutron star or if the star is massive enough, the entire mass of the core collapses into a black hole. So the event horizon is the boundary around the black hole and nothing can escape its gravitational pull. And the whole part of the black hole is called the singularity. Singularity may be indefinitely dense, meaning that all its mass is concentrated into a single point in space with no surface or volume. Or it can be something completely different. Right now, there is no exact definition or function for the singularity point, like it's under study. So the further away from the singularity you are, the longer you live. So like how soon one would terminate on entering the black hole depends on the mass of the black hole. The smaller the black hole, a person, before he or she even enters its event horizon, while one would probably travel inside a supersized massive black hole for quite a while. So the further away from the singularity one is, the longer one can survive. And black hole come in different sizes. There are stellar mass black holes with a few times the mass of the sun and the diameter of an asteroid. And then there are supermassive black holes that are found at the heart of every galaxy and have been feeding for billions of years. So currently, the largest supermassive black hole known is S5114 plus 81, which is 40 billion times the mass of our sun, and it is 236.7 billion kilometers in diameter, which is 47 times the distance from the sun to Pluto. Okay, so as powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. So the next slide, please. Okay, so here I'm discussing the properties of neutron star. Neutron stars are born from massive stars that explode in supernova, as Purvi discussed earlier. So this can be imagined as a cosmic recycling process, like the core of a massive star collapses due to gravity, becoming incredibly dense. So a neutron star is like the dense leftover core of an exploded star. It's mainly made up of neutrons and has a solid crust and a liquid core. It's super heavy. So neutron stars typically form from supergiants with a mass between 10 and 25 times that of our sun. This mass range sets the stage for an intense gravitational collapse. So this results in the creation of a neutron star. So now sometimes these stars turn into pulsars, which are like cosmic lighthouses. Like they spin and send out pulses of radiation at regular intervals. And this creates a kind of a rhythmic light show. So can I move on to the next slide? Okay, so here I am discussing the gravitational wave effects of both the black hole and the neutron stars. So as discussed earlier, neutron star possesses strong magnetic fields and they can also transform into pulsars emitting beams of electromagnetic radiation from their magnetic poles. So whereas black holes are characterized by the concept of singularity, a point in space-time, where gravitational forces become infinitely strong and space-time becomes highly distorted. And unlike other celestial objects, black holes don't have a defined surface like a solid planet. Instead, they are defined by their event horizon, as I said earlier, a boundary beyond which nothing, not even light, can escape into the intense gravitational pull. So neutron stars' gravitational effect is not as strong as that. Neutron stars impact nearby objects but allow light to escape. Gravitational effect near a black hole can generate gravitational waves. And in 2015, the Laser Interferometer Gravitational Wave Observatory confirmed the Einstein theory of general relativity that predicted the existence of gravitational waves. So these gravitational waves were seen as ripples in space-time caused by accelerated masses. So this LIGO observatory consisted of two observatories in the United States, used highly sensitive interferometers to detect minute changes in the length of perpendicular arms caused by passing gravitational waves. So this monumental confirmation came on the 14th of September 2015 when this LIGO observatory observed gravitational waves produced by the merger of two black holes, creating a single more massive black hole. So by the merger of black holes, I mean a binary system, which refers to a celestial system consisting of two astronomical objects that are bound together by their mutual gravitational attraction. And in a binary system, two objects orbit around a common center of mass. The gravitational force between the objects is the dominant factor that hold the systems together strong. So when neutron stars are in a binary system with the black holes, the neutron stars can experience star quakes, means that the neutron star's structure may undergo deformation due to the gravitational forces from the black hole. And as a result of this, the distribution of mass within a neutron star can change. And this change in the distribution of mass can alter the neutron star's rotation. So the immense gravity of the black holes bends the path of the light from objects in the background. So this acts like a cosmic lens and it magnifies a view of the universe. So the next slide, please. So pulsar is a highly magnetized rotating neutron star. It emits electromagnetic radiation around its magnetic poles. When a pulsar is a part of a binary system, its pulse periods can change because the pulsar is in motion around its companion stars. And this leads to variations in pulse periods. So the change in such pulse periods are attributed to the Doppler shift effect. It's like the changing pitch of a siren as it approaches and then moves away. So in this case, it's the pulsar's motion in its orbit causing variations in the observed pulses. So when it comes to the precision of these pulsar pulses, it exhibits an incredible precision. The intervals varies from milliseconds to seconds. And this regularity is a result of the rapid rotation of the pulsar. So there is also this lighthouse effect, which comes from misalignment of the magnetic axis with the rotational axis. So this misalignment causes the beam of radiation to be visible once for every rotation, and it gives the distinctive kind of a pulsed appearance of a pulsar. Next slide, please. Okay, so these neutron stars are also known for their rapid rotation, some completing hundreds of rotations per second. And high rotation rates result from the conservation of angular momentum during the star's collapse. So these neutron stars possesses magnetic fields that range from 10 to the power 8 to 10 to the power 15 Gauss. And born with strong magnetic fields, neutron stars often reach maximum strength during a supernova event. And while some neutron stars maintain strong magnetic fields, others may experience decay or changes due to some astrophysical processes. And the magnetic poles may also not align with their rotational axis, resulting in the complex magnetic field geometries. And neutron star magnetic fields crucially shape accretion disks, which will be discussed later on in a binary system. And this influences mass transfer and angular momentum. Yeah, so thank you, and over to Kavya.
Am I audible now?
Yeah, you are audible.
Yeah. So today we are going to discuss regarding the interplay between the black hole and the neutron star, that is the orbital dynamics. Next slides, please. Yeah. Before studying about the interaction between the black hole and neutron star, we have to focus on the tidal challenges of the black holes. So it undergoes a few astronomical phenomena which we need to study about their fundamental aspects. That is the black hole fundamentals. What are the main aspects we are going to see in this webinar is tidal problem around the black hole, eventually losing the energy when both compact objects are rotating each other in a binary system. Magnetic field distortion is occurred for neutron star, which is due to the tidal forces exerted by the black hole, and the interaction which is leading to the mass and the angular momentum transfer between those two compact objects. Evolution of the accretion process will also takes place, forming the disk around the black hole, resulting the release of tremendous amount of energy in the form of X-rays, radio waves, and as well as EM radiations. Next slide, please. Yeah, what is actually the tidal problem? Tidal problem is nothing but it is simply referred to the tidal forces exerted on an object which is getting very closer to the black hole. It is like these are the special kind of the forces which are having a certain kind of the boundaries around the black hole. It arises due to the gravitational pull on one side of the object significantly experiences stronger than that of the other side. As the object, like a neutron star, approaches a black hole, it experiences a difference in the gravitational pull between the neutron star's nearest surface to the black hole to that of the far side, become extremely large. This will undergo with the significant distortion and disruption to the object, and then it will result a potential tearing it apart in the process called disruption, a tidal disruption. So then, what is the sources of these tidal forces? Where does these will arise? So we normally know that black holes have an immense amount of mass concentrated in a tiny space, creating an incredibly strong gravitational field. And these forces arise from the gravitational gradient that will cause this kind of tidal problem around the black hole. And next, please. Next slide, please. Yeah. Next, we are going to study about the merging event of the binary system of the black hole and neutron star. Let's have a look on the article, a brief overview of black hole neutron star merger system. So this article is published in the July 2020 in the Frontiers by the assistant professor at University of New Hampshire, Durham, United States. The paper simply explores the different types of outflows that the black hole neutron star mergers can produce, so that we will get a certain kind of information where we can extract the information from the observation of the gravitational waves and the EM signals which are emitting by these binary system. It is categorized under three certain conditions, and those are a long in-spiral during which the two objects slowly losing the energy and angular momentum to the gravitational wave emission. And this will further, you will get the information in the next conceptual explanation. And the next category is a merger phase, which will result either the tidal disruption of the neutron star leading to the mass ejection and formation of the accretion disk around the black hole, or it plunges into a black hole, the neutron star completely into it. So according to the paper, first of all, there are normally, now I have discussed disrupting and non-disrupting cases. So according to the non-disrupting cases, the merger ends with the gravitational wave signal, which is practically identical to the binary black hole system with same component of masses and spins. But still the research is in the active area. There's neither mass ejection nor accretion disk, and it is not expected to detectable post merger EM signals. So here we shall study the disrupting type merger event in this webinar. So during the process of orbiting, the black hole and neutron star will radiate gravitational waves. These waves are arised due to the strong gravitational force which is already present in these compact objects, and these originated from the kinetic energy, potential energy, or the energy which is emitting due to their orbital motion. There will be a gradual loss in their energy of the entire system. As both compact objects get closer and closer to each other, their gravitational attraction grows so strong that it will result the warp in the space-time fabric. So a matter from the disrupted neutron star begins to circulate through some kind of the shocks and interaction between the tidal tail of the present in the tidal forces around the black hole, which will again in turn distorts the magnetic field line pattern of the neutron star around it. From this effect, the magnetic field will starts weakening around the neutron star. So after this, the accretion process will start to outflow and fall onto the surface of the black hole, forming accretion disk around black hole. Also, the flow of magnetic field and neutrinos starts to play their own significant role. According to the paper, the magnetic field and turbulence which is causing due to this will grow eventually due to the Kelvin-Helmholtz instability at disk tail boundary. It will also eventually heating the disk and driving the outflow motions. Later, it is also observed that growth of magnetorotational instability will also leads to the increase in the strength of the magnetic field, angular momentum transport, as well as the heating in the disk of the accretion around the black hole. So whenever the neutron star is getting merged with the black hole, definitely the magnetic field strength will goes on increasing. One of the most captivating aspect of the black hole neutron star merger is that the role of the synthesis of heavy metals. So neutron stars are known for their wonderful process known as nucleosynthesis, where the neutron capture process will takes place, which will be the responsible for production of the heavy metals. When neutron star merges with black hole, the intense tidal forces and the heat generated during the event create a conditions to produce that kind of condition will facilitate to produce a certain kind of heavier elements, including gold, platinum, uranium, and etc. So these elements are the integral to formation for the planets, stars, and life as we see on our earth today. Next slide, please. So here we are seeing the simulations which is prepared by the Max Planck Institute of Gravitational Physics in the Potsdam and from the Japan. This picture will show, this picture is the first time modeled by taking a certain kind of limitations about the masses of the black hole and the neutron star. Here they consider the masses of the black hole were set at the 5.4 and 8.1 solar mass respectively, and the mass of neutron star was set only for 1.35 solar masses. These parameter particularly they were chosen because they are expected to turn out that neutron star from the tidal forces of the black hole, and they want to create the accretion process of it. At the last sixth picture, you can see there is an tremendous increase in the um, um, tremendous increase in the tidal forces as well as entire accretion processes, as magnetic field is also increased in the last picture. Thank you. Over to the next participant.
Am I audible?
Yeah, you are audible.
Hello everyone, I am Deeptangshu, and today I am going to discuss about the observational signatures of black hole neutron star binaries. So as of now, only 4 black hole neutron star binary events have been detected by the LIGO-Virgo-Kagra scientific collaboration with a false alarm rate of less than 1 per year. These black hole neutron star observations provide us information on the formation pathways of compact objects similar to binary black holes and binary neutron star mergers. Black hole neutron stars generally emit gravitational waves, X-rays, gamma rays, and electromagnetic waves, and thus can be detected by detecting these waves. So to begin with, let us understand some of the major differences between gravitational waves and electromagnetic waves. Gravity is a weak force, but has only one sign of charge. Electromagnetism, on the other hand, is much stronger, but comes in two opposing signs of charge. This is the most significant difference between gravity and electromagnetism, and is the main reason why we perceive these two phenomena so differently. It has several immediate consequences too. Significant gravitational fields are generated by accumulating bulk concentrations of matter. On the other hand, electromagnetic fields are generated by slight imbalances caused by small, often microscopic separations of charge. Gravitational waves, similarly, are generated by the bulk motion of large masses and will have wavelengths much longer than the objects themselves. Electromagnetic waves, meanwhile, are typically generated by small movements of charge pairs within objects and have wavelengths much smaller than the objects themselves. Gravitational waves are weakly interacting, making them extraordinarily difficult to detect. At the same time, they can travel unhindered through intervening matter of any density or composition. Electromagnetic waves are strongly interacting with normal matter, making them easy to detect, but they are readily absorbed or scattered by intervening matter. Also, gravitational waves give holistic sound-like information about the overall motions and vibrations of objects. Electromagnetic waves give image representing the aggregate properties of microscopic charges at the surface of objects. Gravitational charge is equivalent to inertia. Electromagnetic charge is unrelated to inertia. This is the more fundamental difference between electromagnetism and gravity and influences many of the details of gravitational radiation. But in itself, it is not responsible for the dramatic differences in how we perceive these two types of radiation. The fundamental field of gravity is a gravitational force gradient or a tidal field and requires an apparatus spread out over some distance in order to detect it. The fundamental field in electromagnetism is an electric force field, which can be felt by individual charges within an apparatus. The dominant mode of gravitational radiation is quadrupolar. It has a quadratic dependence on the positions of the generating charges and causes a relative shearing of the positions of receiving charges. The dominant mode of electromagnetic radiation is dipolar. It has a linear dependence on the positions of the generating charges and creates a relative translation of the positions of receiving charges. Now, let us understand a bit about the gravitational waves and its detections. Gravitational waves can be emitted by a set of sources such as relic background, binary background, supermassive black hole binaries, white dwarf binaries, extreme mass ratio in spirals, black hole binaries, and neutron star binaries. When black holes and neutron stars interact with each other, they can get locked in binary systems. They are stuck in a spiral motion across the center of mass of the system. This lasts for millions of years. The black holes or the neutron stars gradually but constantly lose energy in the form of gravitational waves and electromagnetic waves. As they continue to lose energy, their spiral orbits become smaller. This phenomenon is known as inspiral. Their orbital speeds increase as they get closer to each other. Ultimately, they merge in a merger lasting about 1 milliseconds. So some detectors of gravitational waves are pulsar timing, LIGO. So let's know about pulsar timing. It is a gravitational wave could be detected if two or more pulsars show a correlated pattern or of fluctuations in pulse arrival times. Now let us know what is the Laser Interferometer Gravitational Wave Observatory or LIGO. This consists of two facilities in separated locations in North America. Each facility has an L-shaped vacuum tube 4 kilometers long. with masses hanging at the corner and ends of each arm, carefully shielded against vibrations or other outside disturbances. A passing gravitational wave changes the relative distances between the masses in the two arms, which can be detected by interfering laser beams traveling along each arm. Present day sensitivity is at a level where detection of gravitational waves is plausible, if not likely. Let us also know about some of the future detectors. Pulsar timing array. In the next decade or so, it is expected that discoveries of new pulsars, improvement in the precision of pulsar timing measurements, and longer observations of pulsar will result in a dramatic improvement in the sensitivity of pulsar timing to gravitational waves. LISA, Laser Interferometer Space Antenna. This is a space mission planned to launch within the next decade or so. This would place three spacecraft in solar orbits about 5 million kilometers apart. The spacecraft would use laser ranging to monitor their relative separations and thus would be sensitive to charges caused by passing gravitational waves. Advanced LIGO. Continual improvements to the LIGO detectors will result in an order of magnitude improvement in sensitivity over the next few years. At that level of sensitivity, gravitational wave detections are likely to occur on a daily or weekly basis. There is a LIGO project planned for India as well, which will be constructed in Maharashtra, India. Now let us know about X-ray binaries. In neutron star black hole binaries, the outer layer of the neutron stars are stripped off and form an accretion disk around the black hole due to the extreme gravitation of the black hole. The influx of material isn't constant either. As the accretion disk swirls around the black hole, large amounts of heat gets generated due to which high energy emissions in the form of X-rays occur. The extreme magnetic fields generated in the region accelerate the particles to very high speeds, resulting in the production of X-rays. Also, due to the variable influx of material onto the black hole, we get X-ray bursts at the times, and these are called tidal disruption events. Let us know how X-rays can be detected. X-rays can be detected in two different methods. The first method involves a gas chamber filled with inert gases such as neon or argon. As the X-ray photons interact with the gas molecules get excited and they emit electrons. When these molecules return to their ground state, they now emit low energy photons. These photons and electrons are detected using a photodiode to detect the X-ray. The different types of gas field detectors are ionization chambers, proportional counters, and Geiger-Müller tubes. The second method involves a different approach. X-rays are so energetic that they tend to pass through most things, including mirrors. So, X-ray telescopes need to have mirrors that are made of materials capable of reflecting X-ray photons and need to be oriented such that the X-rays hit the mirror at the grazing incidence. Thus, X-ray telescopes use cylindrical mirrors and nest them one inside the other to be able to focus the X-rays onto the detectors. Now let us know a bit about history of X-ray detections and future possibilities. European Space Agency's Copernicus, which was launched in 1972, was one of the first X-ray telescopes. NASA's Chandra X Observatory and XMM Newton have been the flagship X-ray observatories over the past 3 decades and have played an instrumental role in detecting X-ray binaries. ROSAT and Neil Gehrels Swift Observatory have detected numerous binaries over the years. NASA's IXPE, ISRO's ASTROSAT, and soon to be launched XPOSAT will play important roles in X-ray detection in the near future. Presently, NASA's IXPE and ISRO's XPOSAT play a complementary role with each other, where IXPE detects X-ray polarization ranging from 2 kiloelectron volts up to 8 kiloelectron volts, while XPOSAT detects from 8 kiloelectron volts up to 30 kiloelectron volts. Link and Athena will be the flagship X-ray satellites for the upcoming decades and could help us make groundbreaking detections related to X-rays. Now I'll be discussing a bit about gamma ray observations. Black hole neutron star binaries and black holes in general are capable of emitting gamma rays through a process known as Hawking radiation, which was first theorized by British physicist Stephen Hawking. So to understand this better, let us consider an astrophysical scenario as shown in this diagram. The shaded orange region is the non-detection area. So when a primordial black hole lies in this region, its Hawking radiation lies below the sensitivity of modern observatories and is thus undetected. Once the black hole approaches the neutron star and its velocity component is pointing directly towards the Earth, its Hawking radiation is significantly Lorentz boosted, and it might be measured in the mega electron volt range. As this black hole goes around the neutron star, as in the case of a scattering orbit, the velocity component is now opposite to the Earth's line of sight, so a deboosting effect occurs. In this situation, the Hawking emission drops below the gamma ray observation sensitivity and re-enters the non-detection area. So coming over to the detection of gamma rays are generally detected in a similar fashion to X-rays, but since they are slightly harder to detect than X-rays, they require higher sensitivity on the part of the detectors. So the Compton Gamma Ray Observatory, also known as CGRO, was a space observatory detecting photons with energies from 20 kiloelectron volts up to 30 giga electron volts in Earth orbit from 1991 to 2000. The CGRO detected several thousand gamma ray bursts in its lifetime and also conducted some of the first detailed gamma ray surveys of the sky, including the galactic center. NASA's Fermi Gamma Ray Space Telescope has played an instrumental role in detecting gamma ray bursts from black holes. Fermi-LAT and E-astrogram are some observatories capable of detecting gamma ray bursts from black holes and neutron star interactions. The upcoming Cherenkov telescope array will be the most powerful ground-based facility for high-energy gamma ray detection so far. It could play a vital role in detecting Hawking radiation in the future. Now, I would like to call upon Rida to deliver the vote of thanks.
Okay, so hope I'm audible.
Yeah, you are audible.
Okay, so good evening, everyone. We stand before you today with immense gratitude and joy as we express our heartfelt thanks to the Nakshatra Sciences and Collaborative Research Team for providing us with an exceptional platform to delve into the fascinating world of astronomy. Our sincere appreciation goes out to Sitara Srinivasan, the visionary founder, and Sagar JC, the dedicated member of the Nakshatra team. Their unwavering commitment and tireless efforts have played a pivotal role in creating this outstanding learning environment. We are also profoundly grateful for the invaluable guidance and support of our exceptional observational astronomy mentors, Ketan R for his expertise in X-ray astronomy, Saraswati for her insights into astronomical instrumentation, and Kshitij B for guiding us through the complexities of radio astronomy, Yash A for his profound knowledge in cosmology. Your continuous dedication, encouragement, and excellent mentorship have not only fueled our passion for astronomy, but have also provided us with a wealth of knowledge that will undoubtedly open new doors of astronomy. In the wise words of Stephen Hawking, the universe doesn't have behave according to preconceived ideas. It continues to surprise us. Indeed, our mentors have equipped us to embrace the surprises and mysteries of the universe with enthusiasm and curiosity. As we conclude this chapter of our learning journey, let us carry forward the spirit of exploration and discovery. Together, let's continue to explore the wonders of our universe. Thank you.
Thank you, guys. Thank you, Group 7. So that was a very good presentation encompassing so many aspects. I just felt it went a little bit fast, except that the presentation was very good. And I hope all the people here understood. And if you have any doubts or questions, you can ask now. Anyone want to unmute and ask, or you can put the questions in the chat box, anything.
Can you hear me? Hello?
Yeah, we can hear you.
Yeah. So about the nebula, you said the nebula was held under gravitational force.
Yeah, because nebula contains some gases as well as the dust, which has a gravity. So,
So what's like if it's not collapsing into a star? So what's countering the gravitational force to maintain the equilibrium?
the pressure of the gas itself.
Okay.
The gravity and the pressure of the gas, which are both are in equilibrium, so it doesn't collapse. When the further gas, I mean the further clouds gets added, the pressure gets imbalanced and the gravity gets dominated. So it's under its own gravity, it collapses.
Yeah, but
I hope
why is it irregularly shaped? Like I mean, not like a regular structure, then, like spherical
uh,
nebula.
for that, I'm also not very sure about it, but I definitely go through.
Okay.
Okay. Any other doubts? Fine then. So thank you guys for joining, and it was a nice presentation once again. And thank you guys. And please send the presentation PPT file in the group. And yeah, that's it. Thank you guys. Bye all.
Thank you.
Thank you.